This is video 44 in our series on tensor calculus. In this video, we'll develop the syntax used in tensor calculus to represent determinants. The determinant is a function whose input is a square matrix or an array of numbers that we could represent possibly like this with indexes I and j. We could also represent it this way, a with ij with lower indexes, or a ij with upper indexes. Now, these could be tensors or perhaps just systems of numbers using the indexes as indicated. Now, the output of a determinant is a scalar value. So regardless of which of these forms we're looking at as the input, the output is going to be a single scalar value. And we represent that output sometimes as the det of A, or sometimes we put the symbol inside a set of brackets like this, or sometimes if the context is such that there's no ambiguity, we simply represent it as a scalar value like this. Okay, now what you're looking at is what you'd probably find if you looked up the determinant on the internet. You'd find Leibniz formula, and this is written as it relates to a square array of numbers that are labeled with indexes in the upper and lower positions like this. Now, if you haven't seen this before, it's probably very intimidating, and rather than try to describe it in some very minute theoretical terms, what I want to do is just to start by taking the determinant of a 3 by 3 matrix, and then once we've done that, I'll go back and discuss what Leibniz formula is all about. Well, we'll start by representing our array of numbers in a matrix form like this. We have I and j as our indexes, upper lower position, so this is row 1 through 3, this is column 1 through 3 like this. And so all of these 9 elements are going to be the inputs to our function. And the way I learned to take the determinant of a 3 by 3 matrix is this. We first copy columns 1 and 2 to extend the matrix to the right like this. Okay, now we're going to say that the value of our determinant, which is A, is going to be equal to a set of terms added together, and we determine those terms by drawing lines like this diagonal. We'll take the factors A1, 1, A2, 2, and A3, 3. They're the elements that exist along this diagonal line, and we form a product of those three. Then we add the product that's formed by the next diagonal. So this is A1, 2, A2, 3, and then A3, 1. We continue the process. We'll take these elements and form a product. That's A1, 3, A2, 1, and A3, 2. Now we do the same thing in this direction. We take this diagonal, forming a product of terms A1, 3, A2, 2, and A3, 1. Only this time, when we go in this direction, we'll use a negative sign. So now we'll take this diagonal, negative A1, 1, A2, 3, and A3, 2. And finally, this diagonal, again a negative sign, A1, 2, A2, 1, and A3, 3. Okay, and there we have the determinant of the 3 by 3 matrix. Now there are other devices that will produce the determinant of a 3 by 3 matrix, but in the end, all of them, whichever one you use, will produce an expression that looks like this or its equivalent. You're going to wind up in the end with an expression that has 6 different terms, and each of the terms is going to have 3 factors in it, and they'll either look like this or the equivalent of this. So let's talk now about how Leibniz formula applies and works with it. First of all, this thing called Sn is known as a symmetry group, and all it is the designation of a set of numbers. S1 is just the number 1, S2 is the set of numbers 1 and 2, S3 the set of numbers 1, 2, and 3, and so on. Alright, now this symbol out here represents each of the possible permutations that could exist within each symmetry group. So to illustrate that, what we'll do is to say that we're here dealing with symmetry group 3, which is just 1, 2, 3. And this sigma is going to iterate through all the different ways that you can reorder these 3 numbers. For example, we could start with this one. We could then have 2, 3, 1, or 3, 1, 2, or 3, 2, 1, or 1, 3, 2, or 2, 1, 3. Those are the 6 ways that we can iterate the elements within symmetry group 3. So all of these would be our iterations of sigma. So what our formula is telling us is this, that for each of the possible rearrangements of the elements within symmetry group 3, we're going to have a term. And indeed we do. We've got 6 different terms. And for each of those terms, we're going to produce a product. And that product is going to have 3 factors in it. So we're going to iterate this from 1 to 3. And the upper index is just going to be the numbers 1 to 3. And you see that here. In each of these terms, the upper index is just 1, 2, 3, 1, 2, 3 all the way through. And the lower index is going to be the digits of our particular rearrangement iteration, taking digits one at a time. So, for example, our first product is going to use sigma I is going to be 1, then sigma 2 is this, and 3, and that's how we get 1, 2, and 3 down here. And now we look at the second iteration, and that gives us 2, 3, and 1, and so on. In other words, we're forming products in which the lower indexes are just equal to each of these iterations, like this. And you'll see that as you look at each term. And finally, this sign out front is a function that will set the sign of the product based on whether we're dealing with an even permutation or an odd permutation. So in this example, the first 3 of these are even permutations. The second set are odd permutations. So that's why each of these wind up being negative. So that's what Leibniz formula is all about. Now it works for any dimension and it's very interesting, but it's not particularly useful in tensor calculus. So now I want to give you the form in tensor calculus that will give us exactly the same result. Okay, what's this all about? Well, this is our old friend, the permutation symbol that we developed in the last video. And what we're doing here is forming a contraction between this expression and this factor over here. Now, at first glance, it doesn't seem like it's the same thing, because if we're doing a full contraction here, we're going to have a total of 27 products on the right-hand side of this expression. However, remember from our last discussion that of those 27 products, 21 of them are going to be 0. The only non-zero values of E here are going to be those in which the indexes are the digits 1, 2, and 3. Anytime we have a duplicate, we can ignore it because the value of E is going to be 0. So this expression, although it will produce 27 terms, is only going to produce 6 terms that are non-zero. The other 21 are going to be 0. Now, of the 6 that it produces that are non-zero, half of them are going to be positive and half of them are going to be negative. So as we iterate through I, j, and k, we're going to come across each of the 6 permutations that are possible for the digits 1, 2, and 3. So when I is 1, j is 2, and k is 3, this is what we get. When it iterates to I equals 2, j is 3, and k is 1, we get this term, and so on. Well, if you play around with this a little bit, you'll find that by expanding this out, you'll get exactly the same results here that you do in this expression. Now, even though this expression is much more to our liking, it's still not perfect. After all, we've got hard-coded values for these 3 indexes, and that's certainly not perfect for us. So let's see if we can improve on this result even more. Well, consider this expression. E ijk times A2I, A1j, and A3k. What would this expression be relative to this one? Well, multiplication is commutative, so I can change the order of these 2 terms, and I'll get E ijk times A1j, A2i, and A3k. And now, with our rules of tensor calculus, we can rename indexes. So I'm going to rename I to j and j to I. And that will be E j I k times A1i, A2j, and A3k. All right, however, Ejik compared with Eijk are negatives of each other. And that is to say, I can replace this expression, this one factor, with a negative Eijk, and then the other terms follow along, AI, A2j, and A3k. Now, this expression, of course, is exactly equal to this one. So what we can say is that the effect of switching these 2 indexes, the only difference between this term and this one is the order of these 2 indexes. So by switching the 2 indexes on top, I result in changing the sign of the expression. So flipping 1 with 2 flips the sign of the expression from positive to negative. Well, we could go through the same exercise by flipping 1 and 3 or 2 and 3. Every one of those would work exactly the same way. In other words, the indexes on the top of this expression are skew symmetric. Every time we flip the order of these indexes on top, we'll reverse the sign of the expression. All right, with that in mind, then we can write our expression this way. We'd have A times E with RST as upper indexes would be equal to E ijk times A R I, A S J, and A T K. So what I've done here is I've introduced 3 free indexes. These 3 match the indexes across here. Now, because we know that these indexes exhibit skew symmetry, every time I switch the value in one of these indexes up here, I'm going to change the sign of the expression. But the same thing happens over here. If I switch R and S here, I'll switch R and S here, and of course this symbol switches signs every time that happens. So that's why this is an equality. Now the advantage here is that I no longer have any hard-coded indexes. Now the next step in the parade here is that we want to try to express A by itself on one side of the equation. And we accomplish that by forming a full contraction with our new expression here. So we would have A times E R S T, and we would multiply then by E with R, S, and T in the lower position. And of course I have to do the same thing over here. E, I, J, K times E, R, S, T times A, R, I, A, S, J, and A, T, K. Now what I've done is just changed the meaning of indexes R, S, and T from free indexes to dummy indexes on both sides. Okay, now when we look at these two expressions together, what do we see? Well, as we iterate through the values of R, S, and T, we're going to find that there are only 6 combinations where either of these is non-zero. But each time we run into a non-zero value up here, each time we have something that produces either 1 or -1 in this expression, we'll produce the same value here, 1 and -1. So these are either both 0, or they're both 1, or they're both -1. And since we're going to iterate through this in a way that's going to produce 6 permutations that work here, that means that we're going to have 6 non-zero values here. In other words, this contraction by itself equals 6, or it's better expressed as 3 factorial, because that's the number of permutations we can have with these 3 indexes. And that leads us to our final expression. It looks like this. A is equal to 1 over 3 factorial, or 6, times E with I, J, K as upper indexes, times E with R, S, and T as lower indexes, and then our 3 factors of A. There's A, R, I, A, S, J, and A, T, K. Alright, now this is finally what we're looking for because, number 1, it has no hard-coded indexes anywhere in the expression, and it's a full contraction. We have dummy indexes. We've got 6 dummy indexes here, so the whole thing contracts to a scalar value out here on the left. Now, of course, the disadvantage of this expression is that it's a whole bunch of terms. We've got 6 indexes, which means that's 3 to the 6th power, or 729 terms in this expression. But most of them are 0. All but 36 of them are 0. And of those 36, there are going to be 6 duplicates each. And that's why we have to divide this expression by 6 in order to get the right answer for A. Now, of course, because of that complexity, we'd never use an expression like this to actually calculate the determinant. That's not the point. The point is that it is a form that, first of all, gives us the right answer. Number 2, it's an explicit formula for our determinant. And number 3, everything in it is expressed in full-blown tensor calculus syntax. So we can insert this expression into any tensor equation as we need it. Well, let me wind the video down with this final comment. All the analysis we've done so far is with components that are structured with an upper index and a lower index like this. But we said in the beginning that a determinant applies equally well to any two-dimensional matrix. So it would also apply to components that have 2 lower indexes like this, or 2 upper indexes like this. So let me give you the expressions that would apply to each of these 2 forms. Now you can easily go back and look at all the analysis we did with this form and show that everything we did there works exactly the same way for each of these 2 forms. And you can see that everything we said about this result applies equally well to these 2 as it relates to the respective forms. It's just a matter of making sure that we use the correct permutation symbols to match the indexes as they appear in this factor. So here everything's a lower index, so here the indexes have to be in the upper position, and just the converse here. And that's because we want each of the expressions to result in a full contraction, and therefore giving us a scalar value out here. Now, remember that we said that these are just systems of numbers. We don't know yet whether any of these things represent tensors. That's a topic for a later video. But for now, these are the forms that are required to find the determinant of any one of these index structures. All right, let's conclude with a short recap. We started the video by investigating the Leibniz formula, which tells us how to find the determinant of a doubly indexed system such as Aij. We found that it's a matter of forming all the different product combinations of something like this, A1I, A2J, A3K, in which we permute the values of the lower indexes as the 6 different combinations of the index values 1, 2, and 3. So there are 6 ways to order the lower indexes, and therefore there'll be 6 terms that we add together. And when we have an even permutation in the bottom, the term will be positive. When we have an odd permutation, the term will be negative. Now that relationship is captured very nicely by including the permutation symbol EIJK like this. When we do this, we develop a term here, a result that has 27 terms, but because of the permutation factor here, only 6 of them are non-zero. And the permutation symbol will cause the sign to be correct whenever there's an odd permutation of the values of 1, 2, and 3. So this is the correct expression, or a valid expression, for the determinant. We then discovered that the upper indexes are skew symmetric, and we capture that relationship by including this factor right here. So the interesting thing about our relationship here is that both the indexes ij and k and rst exhibit skew symmetry. And in order to accommodate that, we include this factor here for these indexes and this factor to accommodate these factors. So what these expressions tell us is that for each permutation of the indexes rs and t, which are unique, there can't be any duplicates, for each one of those, there are going to be 6 non-zero values on the right-hand side for unique values of ij and k, and half of them will be positive, half will be negative. And so this relationship then gives us the proper relationship between the determinant and its individual components of the second index system. Now we've included all 3 of these forms because each of these relationships are true whether we're dealing with an index system where we have 1 upper and lower index, 2 lower indexes, or 2 upper indexes. And you'll recall we didn't say anything about whether any of these objects are tensors or not, but we include all 3 of these forms just to keep the index structure correct. Here, these are all live or free indexes, and these are all dummy indexes on this side. We then went on to show that we can form these relationships by doing a full contraction of ERST on the left-hand side. We can then form this relationship, giving us the explicit values for the determinants of each form. So what we have here are expressions that give us the determinant values, the correct values for the determinants, using syntax that is completely consistent with everything else we've done in tensor calculus.